like this. This ring system likely contained several rings that were dominated by larger disintegrating asteroids and existed between 740 and 890 kilometers or 460 to 553 miles above Earth's equator. Also, I want to stress that this figure is very well likely to be an underestimate, so the ring system may have been thicker as well. So, how exactly did these rings form? It is believed that for some reason, around 468 million years ago, a large main belt asteroid, perhaps ranging from between 10.5 to 55 kilometers wide, was knocked out of its orbit, perhaps by a large-scale collision. This caused it to go into the inner solar system where it was captured by Earth gravity. While initially having an oblong orbit, it eventually settled into an orbit which placed it below a key area known as the Roche limit. While dependent on an object's density, the Roche limit is an area above a planet's surface within which gravitational forces will always rip apart an object given a long enough period of time. In this case, due to the asteroid's density, the Roche limit was 9,419 kilometers. As a result, beginning around 467.5 million years ago, the asteroid was ripped apart piece by piece until it formed a large debris field which in turn also broke apart to form a distinctive planetary ring system. Since this placed the entire ring system within the outermost layer of Earth's atmosphere known as the exosphere, the drag it created slowly brought these objects closer and closer to Earth until they eventually collided with the planet. This resulted in a cataclysm known as the Ordovician meteor event. To understand this cataclysm, picture this. Looking at the vast size of Arizona's meteor crater, you might be surprised to learn that impact events of a similar energy release occur once every only 6,000 years, although 7/10 of these occur in the vast oceans. Now imagine that instead of a crater this size forming every 6,000 years, one formed every 6 years. Alongside this, asteroids of all sizes suddenly began to pelt Earth at a rate between 100 and 1,000 times higher than is normal. Yet, unlike typical asteroids and meteorites, they collided at far lower speeds of around 7.8 km per second instead of the typical 17 km per second. As a result, many small meteorites, almost all with an L-chondrite composition, were favored to be preserved in sedimentary rock units around the world in what are known today as fossil meteorites. These impacts peaked in intensity during the first 3 million years but remained elevated, albeit at a decreasing intensity, for the following 37 million years. These impacts may be responsible for a portion of an unusual rapid diversification of life known as the Great Ordovician Biodiversification Event, perhaps by causing numerous small or regional level extinctions which allowed new species to develop and fill these same niches which were wiped out. Also, the beginning of the Ordovician meteor event marks exactly when worldwide temperatures began rapidly dropping, going from 26 Celsius 468 million years ago to 15 Celsius 445 million years ago. This eventually created the first phase of the late Ordovician mass extinction due to the widespread glaciation which resulted in this cool period. The existing explanation for this event suggests that the first land plants appeared around 470 million years ago, which soon dominated the landscape and removed large volumes of carbon dioxide, thus decreasing world temperatures. And yet, carbon dioxide levels only decreased from 4,500 to 4,000 parts per million during the Ordovician period. Thus, it also appears that the vast shadow created by the planetary ring system also aided in causing worldwide temperature to drop, although which had a larger impact is still up for debate. I hope that you found today's video especially interesting, and I would like you to let me know in the comment section below if you have a request for me of a specific geologic topic to cover. Also, I would like to thank this channel's patrons on Patreon and channel members on YouTube.